Okay, so just to recap, we've been studying an interacting quantum field theory in naught dimensions. We've been using perturbation theory, which means we make a weak coupling expansion in G. We've also said that perturbation theory almost never works. What that means is if you were to add up all of these terms, you would not get the exact answer. So that's what we mean when we say perturbation theory doesn't work. But we also, I have claimed, and it's a true fact, that summing the first few terms of perturbation theory gives you answers that are extremely accurate and can be compared against experiment. And this is behind the claims that quantum field theory is a remarkably accurate theory. So working within perturbation theory, we've got the expression at the top of the page for the generating function of correlators. And then we were able to calculate what is the correlator of n of our phi fields in naught dimensions. And we've got that formula sitting there. So we have to just evaluate some number of derivatives acting on e to the j squared over 2 alpha at j is equal to 0. But we know what that is. We've studied that problem of derivatives acting on e to the j squared over 2 alpha. This just gives you the free correlation function. And if we've got 2k derivatives acting on e to the j squared over 2 alpha, we know the answer is 2k minus 1 semifactorial over alpha to the k. So using this inside the 2-point function, we got that formula in the black box. And now at the red box, I've just written it out with the first 3 terms. And you can see it's a 1 over alpha minus 15g over alpha cubed plus g squared over 2 times 945 over alpha squared. What we now want to do, we want to reproduce that last red box on the page using the Feynman rules. So let me tell you what the Feynman rules are. So let's say we're going to write down the Feynman rules for the order g to the power of p contribution to the correlator phi to the 2m. Okay, so the Feynman rules for the order g to the p contribution to phi to the 2m. So just to give you some idea, if we're studying phi squared, then we've got m is equal to 1. And if we're looking for the order g to the naught contribution, while looking at the red box above, that would be 1 over alpha. The order g contribution, that would be minus 15 over alpha cubed times g. And the order g squared contribution would be plus g squared over 2, 945 over alpha squared. Over alpha to the 5, sorry, that should be 5. So the rules that I'm writing down now should be able to reproduce these different contributions to phi squared, okay? So now let me tell you what the rules are. I'll just clean this, we don't need this. Let me just tell you what the rules are. So the first rule is that we should draw 2 m dots. And I'm sure you can see that, but let me just labor the point. So 1 dot for each field in the correlator. Okay? So there's 1 dot for each field in the correlator. And then we draw P vertices. This is for the order g to the p term. Each vertex, so the vertex looks as follows. The vertex is 4 lines meeting at a dot. Now, why do we have 4 lines meeting at a dot? Well, think about the action, which was alpha over 2 phi squared plus g phi to the 4. So this, here you've got a 4 in the interaction. Okay, there's a 4. And here you've got 4 lines meet. Okay. those 4s are related. If you had a phi to the 6 in your interaction, you'd have 6 lines meeting. If you had a phi cubed, you'd have 3 lines meeting. Okay. Now, and then the last rule that I'm going to say is you join dots and vertices in all possible ways. Okay, so now let me just make a comment. I'm sure when you look at this, it looks like I'm making the rules up, and the rules are made up. I didn't make them up. Feynman made them up. So this is just a diagrammatic notation to reproduce the calculation that we did in the red box. So what you should try to do now is don't worry about where the rules came from. Just make sure that you understand what the statement of the rules is and how to use them. And you'll be able to check that it does give you the correct answer in some simple cases, and then use it in other cases where the calculation is too complicated to carry out without the rules. So the rules are going to simplify our life a lot. It's just a diagrammatic notation that was invented to really simplify the calculations of quantum field theory. So don't try to understand where they come from, just try to understand what they say. So let's start off, let's look at phi squared, and let's look at the order g to the naught terms. Well, in this case, we're talking about m is equal to 1. So we need to draw 2 dots. So I've got 2 dots, and we need no vertices, okay? And we need to join those 2 dots in all possible ways. Well, there's only one way to join the 2 dots, and that's what it is. So that was the order phi squared. This was the order g to the naught contribution to phi squared. Now let's look at phi squared, and let's look at the order g terms, okay? So again, 2 dots because we're looking at phi squared. But now we've also got a vertex. And we need to join things in all possible ways. Well, the one thing that we could do is we could choose to join these 2 legs on the vertex, join these 2 legs on the vertex, and join the dot as we did it before. That's a perfectly valid thing to do. Now, let me just make a comment. If you've got a vertex and you want to close the legs, you might have thought of closing the legs like this, or you might have thought of closing the legs like this, or there's even one more exotic possibility where you close the opposite legs with each other, okay? So these are the 3 ways of closing the vertices, the legs on a vertex. In fact, these are not distinct. You won't count these as different diagrams. There's just one diagram that you'll draw, okay? And that's the diagram that I've drawn over there. Again, when we start to translate these rules into mathematics, we're going to want to reproduce what's inside that red box. So it's not arbitrary. I'm inventing a set of rules that is going to give me what's inside that red box. And for now, I'm just telling you what the rules are. So just accept what I'm saying. What I'm telling you is you need to join the 2 dots and the vertex in all possible ways. And the different ways of joining the legs on the vertex with each other are not distinct. If I now want to join these 2 dots and the vertex, I could, well, join 1 dot to a leg of a vertex, join that dot to a leg of a vertex, and join the remaining 2 legs of the vertex to each other. Here again, you might think that there are a number of possibilities. You see, so we could have this, what we've just drawn, but you might think that there's a distinct diagram where we do this. We join those 2 legs, we join this one there and that one there, or there's even another diagram where we might join this one over here, that one there, and then connect that one over there. In fact, once again, all of these different ways of drawing things are not distinct diagrams. So that in the end, only the two diagrams that we've got here is what we would keep. So this is the phi squared order g to the naught terms. Let me just tidy up. Phi squared and order g, what is it? It's this plus that. Okay, just those two diagrams. Okay, now let's look at phi squared and order g squared. So now what do we have? Well, we have the two dots because we've got phi to the 2, so one dot for each field in the correlator, two dots, but we've got two vertices, which means we've got that and that. Now try to join these up in all possible ways, and I'll give you a little hint. When you do this, you should find that there's a total of 7 different diagrams. So see if you can get those 7 diagrams. Once you've got those 7 diagrams, watch the next video.